So, guided practice 5.7 looks again a second look at the mid-segment theorem, but we are going to move into the triangle proportionality theorem, and that's going to be the major focus of this lesson, along with the proportional ratio that's formed by parallel lines. So we're going to be looking at proportionality as it relates both to triangles and parallel lines. We're going to start with the mid-segment of a triangle. So let us take a look at the mid-segment of a triangle again. Let's refresh our memory. Again, the mid-segment of a triangle joins the midpoints of two sides of a triangle such that it is parallel to the third side of the triangle. So you'll remember we did some problems related to the mid-segment. We've got a couple of triangles drawn here. We'll do a few more problems just to get warmed up. Okay, so problem number 1. Find the value of x. Now let's be clear why this is a midpoint, because it is between two congruent segments, and on this side, this point is also a midpoint because it's between two congruent segments. Notice the congruent segments from side to side are not necessarily the same length, but on each side we have midpoints, and this line is a mid-segment. So it is therefore half the length of the third side, so that means x equals 12. Here, again, this is a midpoint on the left, this is a midpoint on the right, so this is a mid-segment, and its length, or 2x minus 14, has to be 1/2 of the length of the third side, which is 24. So 2x minus 14 has to equal to 12, and that makes 2x equal to 26, or x equals 13. Okay. Hopefully that is pretty elementary algebra. And if we plug 13 back in here, we get 2 times 13 is 26, minus 14 is 12. Okay, let's go down to the third sample problem. Find the value of x. Again, we can confirm we have a mid-segment because we've got midpoints on both sides, and we know that this length has to be 1/2 of 10x minus 30. Another way of saying that is to say that 2 times the mid-segment length, or 2 times 2x plus 18, has got to equal to 10x minus 30. Okay, now let's solve this by distributing the 2. We get 4x plus 36 equals 10x minus 30. Sort of running out of space here, so I'm going to conserve space and just sort of skip ahead. I've got 6x equals 66. That makes x equal 11. Well, let's just double check, make sure that works. Make sure I did my math correctly. So we've got 22 plus 18, which is going to give us 40. And then I've got 110 minus 30, which is going to give me 80. Okay, so it does double check. I've got my mid-segment half the length of the third side. Okay, let's move on to the next problem, and this is another coordinate geometry problem. Okay, so we're given that line or line segment BE is parallel to line segment CD, and we've got it drawn here in a coordinate axis. Now we're being asked to use coordinate geometry to prove something about the ratios of the sides that are created by the intersection of these parallel lines with other lines. So let's take a look first at what's happening here. So we've got EB parallel to DC. We're told they're parallel. How do we know that they're parallel? In other words, they look parallel. But how on this coordinate axis can we confirm that these lines are parallel? Well, I hope you remember this is also something I think you learned in Algebra 1, that parallel lines on coordinate axes have the same slope. Okay, I hope that sounds familiar. But if not, then it's something new for you and you need to know it. Parallel lines have the same slope. So let's go ahead and let's double check that. Let's check the slope. Let's check the slope for EB and the slope for DC. So what is the slope of EB? It's rise over run, right? So let's go ahead and check that. Rise over run. So we've got 1, 2, 3, 4, 5, 6. And now we're running backwards, so we've got a negative slope, right? It would be negative 1, 2, negative 1, 2, 3, 4, 5, 6, 7, 8. Okay, negative 8. So 6 over negative 8, which is negative 3/4. So the slope of EB is negative 3/4. Now let's check the slope of DC. And again, let's do rise over 1. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. The rise is 9, and the run would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But negative, because we're going to the left. So negative 9 twelfths, it also simplifies down to negative 3/4. So we can confirm both lines are actually indeed parallel because they have the same slope. Okay, so now that we know they're parallel, what else is happening here? Well, this pair of parallel lines is intersecting two other line segments, DA, the horizontal segment here, and AC, this vertical segment there. And actually, they do form a triangle, right? We've got ADC, which is one big triangle. So you can look at this, if we sort of put this on our side, as being a triangle, where we're drawing a line segment that intersects two of the sides, such that it is parallel to a third side. But unlike the mid-segment theorem, this is not a midpoint, right? You can see it's not in the middle. In fact, it's closer to point D. E is closer to point D, and B is closer to point C. But even though it's not a mid-segment, there still is a proportion equation that is true. EB is no longer going to be half the length of DC, but it's going to be some kind of proportion of DC. So let's go ahead and let's take a look at what we're supposed to prove in this one example. And this is the equation. We have to prove that AE over ED equals AB over BC. So to use coordinate geometry, we're simply going to count our boxes up. So AE, the distance from A to E, is going to be 1, 2, 3, 4, 5, 6, 7, 8. So AE equals 8. ED is 1, 2, 3, 4. And AB, let's calculate AB. That distance is 1, 2, 3, 4, 5, 6 over BC, which is 1, 2, 3. So is 8 over 4 equal to 6 over 3? Yes. They're both equal to 2. So we were able to use coordinate geometry to prove this statement. That is true about two parallel lines. So in this case, at least, we showed that AE to ED, the ratio of this to this, is the same thing as AB to BC. So it turns out that that ratio equality is always true in triangles. And we're going to see some of those problems next.